Hey everyone, this is Physics 1C for March 31st. We're talking about RC circuits. I started the lecture without starting a recording, so this is the type of circuit we're talking about. We said that if you apply the loop rule around a circuit like this, you get an equation like this, and we discussed why this negative sign shows up. But then after we got that equation, here we are, and we're using it to solve a differential equation that comes out of this, and this is where we are right now. Okay. All right, so there's our equation. And now we want to do what Matthew said. We want to integrate this. Actually, let me erase this real quick. Equals integrate. So we're going to integrate both sides here. The left-hand side is pretty simple. This is just going to become negative. Well, now I need to tell you something about time and the integration variables here. Our capacitor started off with a charge of 0, and we're going to charge it up to some arbitrary charge that we're going to call Q prime. And then the same thing over here, we're going to integrate from 0 to some time t prime. The left-hand side of this equation is just going to become negative t prime over RC. The right-hand side of the equation, if you do this integral right here, what would you get if you did this integral right here? Yeah, the natural log of all the stuff in the denominator, right? So it's going to be the natural log of like that, right? Does that look okay to you guys? This is physics 1C, so you guys all should already have known that this part. I know I've taught this before, and people have told me they didn't know this, but the integral of this is equal to the natural log. That's something you guys have seen before, right? Have some of you guys not seen that before? When do you guys learn it? We're just ultimately trying to find this. Again, I'll just remind you, we're looking for the charge as a function of time, right? So what I'm doing here is just to make sure that the variable of integration isn't the same as the limit. I chose Q prime, which is like a dummy variable that's going to go away later. We'll just drop the primes, if that makes sense. Okay, let's fill out what this is. The natural log of this is going to be the natural log of I don't know if I don't want to skip too many steps. So it's going to be like Q prime minus CE, right? And then minus, we plug in Q equal to 0, we get the natural log of just CE. But then using one of the log rules, we can say that this becomes a ratio of Q prime minus CE divided by CE. And then to get rid of the natural log, we raise both sides to the e power. So the left-hand side now becomes e to the negative t over RC is equal to, the right-hand side just becomes, oh, I could leave the primes in here, Q prime minus CE over CE. Our goal is to isolate Q prime right here. If we do that, then we're going to get something like this. We'll get what CE e to the negative t over RC is equal to Q prime minus CE. And then we add this one to the left-hand side. So I think finally we're going to get something like, I'm dropping my primes. We're finally going to get something like Q prime as a function of time is going to be equal to CE minus CE e to the negative t over RC. And the final line, I'm going to drop all the primes. It's going to be Q of t. It's going to be equal to C times E multiplied by 1 minus e to the negative t over RC. And that gives us the charge as a function of time on the capacitor. If you remember from before, I said that the maximum charge on the capacitor was equal to Q. So the other way to write this would be just say that the charge as a function of time is basically equal to Q, the maximum charge. We could even call this Q max if we want to, multiplied by 1 minus e to the negative t over RC. This one kind of looks nicer because this little term right here is just a fraction, basically between 0 and 1, okay? Because e to the negative t over c, this will always be a number that's less than 1. So, yeah, we can look at some boundaries and stuff for this. That's our equation. Does that make sense so far? Anyone have any questions? So what does this curve look like? If I want to plot, and I have a plot over here that I'll show you, but I'll also plot it by hand because I think it helps to see these things, at least at first by hand, before you see the answer. If this is charge and this is time, what's the charge at q equal to 0 equal to? What's q of 0? It's 0, right? Because if you put, if you plug in t equal to 0 in right here, you get 1 minus 1. That's 0. So yeah, you get 0. So we know we start off at 0, right? What about if I take the limit as t goes to infinity? What does q go to? What's q of infinity, basically? What is this term? Oops. What does that term right there become if you put in infinity? It becomes 0, right? So what's q of infinity equal to? Yeah, this is just equal to the maximum charge on the capacitor. So now if I want to plot this, we know that there's eventually going to be some value that it reaches. That value is going to be Q max. Here, I don't want to write it right there. Right over here. This value is going to be Q max. I'll just write Q. And now if we plot our curve, it's going to look something like this. Right? Does that make sense to you guys? What about the current? If I know this, can I find the current as a function of time? What do I do? Take the derivative. Yeah, so if we take the derivative of q with respect to t, we're going to get, the first term is going to be the derivative is 0, right? This term right here is CE, which is a constant, times 1, so a constant, so you get 0, right? When I take the derivative of this term, I'm going to get 1 over RC, so I'm going to get this, is what I would argue. You get E over R, e to the negative t over RC. That ends up being the current as a function of time in the system. What's the current at time equal to 0? Yeah, it's E over R. This is going to be, we could call this the maximum current if we want to. And what's I of infinity? So now if I plot charge as a function of time, or sorry, current as a function of time, oops. We know that the current starts up at a maximum. This would be I max. And it basically does something like this. It asymptotically approaches 0. Now my drawing is not so great, but again, I think it's important to see things drawn out before you see like what the answer is. But I do have a better picture of it right here. Oops. Need to come down here and click right here. There we go. That is what the current as a function of time looks like, and that's what the charge as a function of time looks like. The current decreases exponentially with time as the capacitor charges, because once the capacitor is fully charged, it effectively represents an opposing EMF to the battery, so no longer, you can't have any charge flow in the circuit anymore. But yeah, that's our picture. We're going to talk about some other features of these. I'm going to show you a little bit of a demo of this real quick. As much of a demo as I can show you on the internet. perfectly fine. Okay, so this allows us to basically connect kind of simple circuits right here. So what we're going to do is we're going to take a battery and we're going to connect it to... Hold up, this one doesn't actually have capacitors in it. Oh, it doesn't. I have to go to the other one, my bad. I have to go to the AC kit. This one. Okay, we're going to take a capacitor. We can change its capacitance if we want to. This one has a capacitance of 0.1 farads. Okay, and we're going to connect it to a battery. So there's our battery. We can also change the voltage of the battery. It's right now 9 volts with 0 internal resistance. That's what the ohms there is. We're going to connect it to a resistor. And we can see the resistance of this is 10 ohms. I want to show value on all these actually, so that we can use them later to do some calculations. All right, and then we'll just connect everything up. So we got a wire going between here and here. We'll have some wires down here. And then we'll throw a switch in the system. The switch is open now, but we can close it. Here. So there's our system. How come it stopped showing values? Okay. So if we turn on the current right here so you can see the capacitor currently has no charge, right? If I close this though, see how the capacitor charges right up like that? But notice that it took some amount of time, right? And I can show you one more time. I think I can discharge it like that. If I close the circuit, it takes some time for the capacitor to actually charge up. It doesn't charge up instantly. And then once it's charged, it'll hold the charge. And we can even discharge it if we want to. I would need to add another piece into this circuit real quick here. It would be if I can just move everything down. I'll just move it down like this, I guess. So if I add another piece of the circuit here and give the capacitor the ability to discharge itself, okay, by doing like this and like this and like this. Yep. So now the capacitor has no way to get rid of this energy that it has stored in it. But if we create a path around like this, it can discharge itself like that. That doesn't happen instantly either. It takes time for it to discharge. We can open this again, close this one, we can charge it up. And then if we want to, we can discharge it like this. The energy that's contained in the battery is used to, the energy from the battery right here can be used to charge the capacitor. Oh, whoops. Let's leave both these open. There's no resistance on the external side. That's why it started burning. So you can close this and charge this up. The capacitor stores energy now, right? And if you want to dissipate that energy, you can discharge it, and then it uses up all of its energy, and that energy goes into the resistor in the form of heat or something like that. That's an RC circuit. That's basically the way that it works. We can even plot voltage. I don't know how well this works. I've done it before, but I don't remember. If I plot the voltage as a function of time on this guy right here, those little wires are kind of annoying, but if I now close this, oh, not this one, whoops. I'll leave this one open first. And let's discharge this. Okay, so we've got our capacitor. If we charge it up, you see how you get that rising feature right there, and then it kind of narrows off. And then if we want to, we can discharge it, and it'll decay down like that. You can just repeat this process over and over again. You charge it, you get this rising current, this kind of exponential rise until it, the situation's out, and then we can discharge it, and it'll be exponential decay, going down like that. Does that all make sense to you guys? Do the same thing with the current if we want to, using this other meter. Where's the ammeter at? Oh, I just clicked this. Oh, there it is right there. Okay. Oh, it doesn't have a... Oh, there it is. Never mind. Disconnect, switch. junction. What I want is to get this one, current chart. If I go over here and I put this one to there, and then we put both of these right by each other, you should be able to see the inverse relationship. Nope, not if I do that way though. This way, discharge. Okay, let's try this again. So no current right now. I feel like the current's too small for it to see it here, so we probably have to go down on our scale a little bit. Wait, am I zooming in or out here? I want to go in, right? Okay, let's try this. Oh, it's not actually on the circuit. Is that what I need to do? There we go. Okay, let's, here, open this up, discharge it. Now if we close it, the current started off negative. This is weird, there's only one thing to connect right here. I'm worried about how it's actually doing this. Let's try this again. Discharge capacitor. Close this. The current is going to 0. Oh, it's just starting off at negative maximum. That's fine. I bet if I put it over here. Here, let's restart it. So, discharge capacitor. Here we go. Yeah, so the charge builds up while this falls down. And we can show it over and over again by just doing this. Each time we discharge it, you're going to see that same feature. The current's on the bottom, voltage is on top. Voltage is basically also a representation of the charge too, right? I should have said that. It was a nice exponential increase and exponential decay for the current. Okay, hopefully that was helpful. Is that helpful to you guys, seeing that? So you guys can feel free to play with those kind of circuits and, you know, learn something about them. Okay, any questions before I keep going? I'm going to mention something about what's called the time constant now. Any questions? So this quantity, R times C, all right, the resistance times the capacitance, it shows up right there, right, in both equations, underneath the time, right? So an easy way to describe what's going on in a circuit like this is to simply multiply those two quantities and get an idea for the time that it takes to actually charge up, right? And, you know, you can use the quantities, for example, like we have over here. So if we go back to this guy, oh, it's in this thing, isn't it? Okay. So of course it doesn't want to keep showing me values for some reason. I don't know why. All right. Show value. So 10 ohms times 0.1 farads. Those are the values that we have in this little thing right here, right? So if I do tau is equal to 10 ohms times 0.1 farad. That's a gigantic capacitor, by the way. 0.1 farads is huge. Then I get a time constant that's about, what, 1 second, right? Now, how do I know it's seconds? Well, if we look at the units, the unit of ohm is a volt divided by an amp. And the unit of a farad is, well, you can use this equation. C is equal to Q divided by delta V to get that the unit of capacitance is basically coulombs divided by volts, right? The volts cancel out, but the other thing is that the other unit you could use for amperes, right, would be coulombs per second, right? So we could replace this guy with coulombs per second, and you see that this gives you the units of a second, right? Because the volts cancel, the coulombs cancel, and you have to just 1 over 1 over a second, so you get a second. So we call this the time constant. Does that mean that it takes 1 second for the object to actually charge up? No. If we investigate our equation up here, so we look at our equation that we just wrote down. This works for either of one of these. Our equation says that Q of t is equal to Q max, which I'll just call Q, multiplied by 1 minus e to the negative t divided by RC. But we're saying this RC quantity, we're calling it equal to tau, right? So you can either write tau down here, or you could write RC, whatever you want to do. I'll keep writing it as RC, but understand that sometimes you'll see it written as negative T over tau. So what is Q after one time constant? Can you guys calculate that really quickly and tell me what it's equal to? If I put 1 tau in here, that's like negative RC over RC, right? Which is just equal to negative 1. Okay, what's that equal to? You guys with me here? Can you calculate that? What's that equal to? You can either type it in the chat or just cue your mic and say something. Yeah, something like 0.63Q, right? Okay, so one time constant is the time that it takes for the capacitor to charge up to 63% of its maximum value. That's what that means. So one time constant, 1 tau, this is the time constant, right? So 1 time constant is the time to charge the capacitor to 63% of the maximum charge. And if we look up on our graph right here, that's going to be somewhere like, I don't know, maybe like right here-ish, right? That could represent 1 tau. Okay? And at that point, it would be at about 0.63 of Q. Right? That's what that means. 1 time constant is the time to charge the capacitor to 63% of its maximum charge. Okay? Does that make sense to you guys? We can also calculate things like Q of 2t, right? That's going to be Q times 1 minus e to the negative 2, right? And you can do Q of 3t, etc. We can calculate all of these things are going to be equal to, right? And if we do Q of like 10t, for example, okay, what are these all equal to? I'm just going to do this real quick here. So it's 1 minus e to the negative 2. That's 86%. It's so weird how quickly I can lose this pen. There it is. So this one is 86%. So this is 0.86. 3 tau is 1 minus, this is times Q, e to the negative 3. It's already at 95% here. And if you do 10 tau, it's going to be pretty much fully charged at that point. This one is 0. 1, 2, 3, 4, 5. Q. At this point, it's effectively fully charged. Now, I'm not saying there's something special about 10 tau, but you should pretty quickly get the idea if you look at like this line right here, that even after 3 time constants, it's already at full charge, basically, right? It's basically already fully charged up at that point, right? 95%, it's pretty much fully charged, right? So if we come back to our animation right here, and you just try to count how long it actually takes to completely charge right here. So I'm going to click discharge, right? And I think we can even see it down here on this graph, actually, if we want to. So if I discharge the capacitor right now, we can see how long it takes to get there. And you'll notice that this is about 460, and that's about 463. Did you guys see that? I'll do it again. Can I make this any bigger? I don't know. Okay, I'm going to discharge the capacitor again. And just watch how long it takes. It takes about 3 seconds. You can even count if you want to. It's probably easier to just count 1, 2, 3, but you'll notice that the size of that graph is it takes about 3 seconds to get from here, that's 484, up to here, which is about 487. About 3 seconds and it's fully charged. Does that make sense to you guys? you can get a general idea of how long it takes to charge by simply taking resistance and multiplying by capacitance. Do you guys understand? So what would happen if I increase this? Okay, what's going to happen to the time constant if I increase this by a factor of 10? So it's 100 now. What's the time constant now? You guys want to type in chat? What's the time constant now? 100 ohms and 0.1 farads. What's the time constant? What's the answer, though? This is extremely simple. You take the resistance, you multiply by the capacitance. What's the answer? 10. 10 seconds, right? It should take 10 seconds for this thing to do what? What does that mean? What does the 10 seconds represent? Yeah, but how much charge is going to be on the capacitor after 10 seconds? So 63%, right? So about how long is it going to take to be fully charged? $30 seconds, right? Okay, let's see if that's true. I'm going to close this now. Notice it's charging much more slowly. This graph is very gradual now. It's slower. Just by changing resistance, it's slower. Do you guys get the idea? It's like time. You're controlling time in a circuit by simply modifying one of these two values. Do you guys understand? Do you understand the power of that? The ability to take these devices and put them in a circuit and have that circuit have the ability to have a time control associated with it? Does that make any sense to you guys? Like, you can control, like, you know, how long it takes for this object to charge up, which means you can control how long it takes for, like, a light bulb to light up in the circuit or something like that, or a windshield wiper to go off. You control the time simply by changing these things, right? If I change the resistance back down to, like, 25, or let's say here, we can increase both of these, right? I can make the capacitance also a lot bigger. If we double it again, we're now at 0.2, and we're at 100. You can see there's actually more charges on here now too. And now if I open this, discharge it, and then close it, it's now going to take about 60 seconds for it to get to 63% of the charge. It'll take about 180 seconds, or almost 3 minutes, to completely charge this thing up now. So now you have this very gradual charge flowing onto your capacitor now. That's what capacitors can do. They can regulate time inside of a circuit. All right. Do you guys have any questions?
What are some other applications of this besides the ones you already mentioned?
Okay, so within this particular system, where you just have a resistor, a capacitor, and a battery, okay, just a battery, right? They're very limited, okay? And that's because you need something like this. So is the circuit okay to show you this, how this is going to work? So this right here is how most power supplies actually work. Like when you plug something into the wall in your home, it is something called alternating current. And what that means is that this battery provides direct current. That's what we're talking about in this chapter, right? Direct current. The current only flows in one direction, right? And because it's a direct current, eventually that current stops flowing. So there's some limitations to what you can do with this, all right? So if I split this junction now, though, oops, split junction, open this. Now what I'm going to put in here is an alternating current voltage. All that this thing does is it applies a voltage. I can even show you what it does. It applies a voltage like this. Can you guys see that? Sinusoidal voltage, perfect sine wave voltage, okay? Sometimes the voltage is positive, sometimes the voltage is negative, right? That's just the source right here, okay? If I put this into my circuit, okay, and then I go back and again I put my voltmeter on this guy right here. Now what happens? If we watch what happens to the capacitor now, and I'm gonna make these a little smaller now, just so that it's not gonna oscillate as fast as we have 0.1 before, right? So 0.1, and let's change the resistance to back to, like, I don't know, 50 ohms is probably fine. Okay, so now watch what happens to the capacitor. it charges up, and then it discharges, and it charges up, and it discharges. I'm going to have to make this bigger. Here, let's open the circuit. Let's discharge this. We're going to have to make this bigger, I think. Okay, there we go. Here. Let me try this again. There we go. It's kind of doing it. Maybe I need to lower the resistance. That's what I want to do. Okay, there we go. So you can actually see what's going on. And then I want to open this. I want to discharge this. I want to close this. Okay. So what you're looking at now is what a capacitor does inside of a circuit that has an alternating voltage. Can you see how it behaves quite a bit differently now? It doesn't really stop the charges from flowing. It acts like kind of like a spring that absorbs the energy of the current and then reflects it back in the opposite direction. Can you guys see that happening? Can you see how one side's positive and then it becomes negative and then it becomes positive and then it becomes negative and then it becomes positive and then negative? Does this motion like look like something you guys have seen before? This type of motion of these charges, does it look like something you guys have seen before? Can you think of any mechanical systems that behave like this? A pendulum, right? A pendulum swings back and forth and back and forth and back and forth. Positive angle, negative angle, positive angle, negative angle. What else? What else have you seen that acts like this? Anything you guys can think of? What other things have you seen that act like pendulums? Yeah, like a mass on a spring behaves exactly like this, right? If you think of the charge on the plate as being like the x-coordinate of a spring, the x-coordinate's positive, and then it's negative, and then it's 0, and then positive, and then 0, and then negative, and then positive, and then 0, then negative. You know what I mean? It's like oscillating back and forth, basically, right? So another application of this, to answer your question, is when you construct a circuit like this, it has this type of oscillating frequency that occurs, and this type of a circuit can be tuned into a radio station, or it can be tuned into a Wi-Fi router, right? Like in your phone, when you connect to your Wi-Fi router, what physically is happening inside of your phone is the size of the capacitance is changing. And if you make it really small, for example, look what happens to the oscillation. It changes a little bit. If you make it really big, now you can get even more charges on here. And then if you also can, you saw before that if I lower this, now all of a sudden the frequency is different, right? Each of those different frequencies, the rate at which the thing is charging, discharging, charging, discharging, that rate is directly connected to the frequency of the Wi-Fi signal that you connect to, or when you tune your radio to 106.7 megahertz or something like that. And by alternating these things and by changing that internal frequency within the system, you can tune into a radio station, or you can tune into a TV station, or you can tune into a Wi-Fi signal. So that's another application of something like this. Does that make sense to you guys?
Yeah, I think.
Sure. And I want to say one other thing about what this thing is doing. This guy, okay, he only pushes in one direction. You know what I mean? He pushes this way and then he stops. That's it. He's done. This can only push in one direction, right? The main difference between a battery and an AC voltage source, which is like your wall socket, is that this one pushes forwards and then backwards, and then forwards and then backwards. Can you see why they call this electromotive force? Does that make sense? Why they say that this thing provides an electromotive force? Because this thing pushes, and then it pushes this way, and then it pushes that way, and then it pushes this way, and then it pushes that way. Like a force, basically, right? But if you look at what we've been discussing in this class today and the last week or so, we're looking at a battery that only pushes in one direction. Can you guys tell the difference? Can you see how it's kind of somewhat connected to physics 1A in a way? I mean, not just somewhat, it's exactly connected to physics 1A. All this stuff, these forces and things, they're all the same. Just one is gravity and one's electricity. It's just slightly different. But... okay. It is now 3 o'clock, so it's a good time. I was going to take a break a second ago, but we'll take a break now. We're going to come back, and when we come back, we're going to do this problem here. So if you want to look at it, you can. I'm going to paste it. Whoops. I'll paste it down here, and then we will take a break. I'm probably going to close the stream too, so I can possibly restart my computer and close some programs. That's what we're doing when we come back. We'll say break until 3:15. And if you do have any questions, just let me know. I need to stop recording.